welcome to the next session of Strength of Materials. In this session, I am going to take up the second numerical on Macaulay's method. Let's get started. A beam of 3 meters span is loaded as shown in figure below. Calculate deflection at P and Q and slope at A. Take E into I as 8400 into 10 raised to 8 Newton mm square. There's a hyphen here. E into I. This term has a particular name. It is called as flexural rigidity. The term E is called as Young's modulus and I is called as moment of inertia. When the two terms are written together, it is called as flexural rigidity. Now let's start with this numerical. This is the beam given to me. If you can observe, VA and VB is directly mentioned, so I'm not going to draw the FBD. I am going to directly start with drawing the section diagram. I'm going to start by drawing the slider on this beam. So this is my point A, reaction VA. At B there is a reaction VB. At point P there is a load of 60 kN in upward direction. At Q there is a load of 60 kN again in the downward direction. So let us hold a slider or section XX at a distance of say X from the end A. From the point P it will be X minus 1.5 and from the point Q the distance will be X minus 2.25. So this is how you are going to draw the diagram. Now I will start with calculating VA and VB. So I'll first write down the condition of equilibrium. Summation of force in y direction is equal to 0. Any force going upward will be considered positive. I have VA going upward. I have 60 going upward. I have 60 going downward. And I have VB is equal to 0. So I have VA plus VB is equal to 0 because this plus 60 and minus 60 gets cancelled. So I can also say that VA will be minus VB. This is my first equation. The next equation that I am going to write is summation of moment about point A is equal to 0. Clockwise moment is positive. So when I talk about point A, 60 will turn anti-clockwise. So I have minus 60 into 1.5. I have this 60 which is turning positively because it is in the clockwise direction. The distance is 2.25 and last I have VB turning anti-clockwise. So I have minus VB into 3 is equal to 0. When I solve this equation, I get the value of VB as 15 kilonewton. From this equation 1, I get VA is equal to minus 15 kilonewton. So these are the two values that I have obtained for the support reaction. Now these values I am going to write in this diagram. VA is minus 15 kilonewton and VB is 15 kilonewton. Next I am going to write the moment curvature equation. I have mx is equal to EI d square y by dx square. Now since the section is over here, I'll have VA turning clockwise. So the value is 15 into x from 0. Okay, I'll write down here x is 0, x is 1.5. Here at Q x will be 2.25 and at B the value of x will be 3. So these are the values. So I'll take the first one between 0 to 1.5. Next I have 60 turning clockwise, so I'll have plus 60 into x minus 1.5 from 1.5 to 2.25 and last I have the 60 turning anti-clockwise, so it is minus 60 into x minus 2.25. It starts from 2.25 and ends at 3. So this is my first equation. This is my moment equation. Now I am going to integrate twice to get the slope and the deflection equation. So I'll have therefore from here I have EI dy by dx is equal to, first I'll write down the constant of integration, that is C1. Then I'll write down 15 x square by 2 from 0 to 1.5. Next I have 60 into x minus 1.5 square by 2 from 1.5 to 2.25. And last I have 60 into x minus 2.25 the whole square by 2 from 2.25 to 3. This is my second equation, which is my slope equation. And last I'll write down the deflection equation from here. EIY is equal to C2 plus C1x minus 15 into x cube upon 6 from 0 to 1.5 plus 60 into x minus 1.5 cube by 6 from 1.5 to 2.25 and minus 60 into x minus 2.25 cube upon 6 from 2.25 to 3. This is my third equation, which is my deflection equation. Now I need to calculate the value of C1 and C2. In the previous session, I just forgot to mention why I'm writing the constant of integration at the start. If you have already gone through the lecture, you have already understood that when I calculate the slope and deflection for a particular point on the beam, I will always consider up to a particular point. For example, if I say for the point P, your x is 1.5. So when I calculate the slope, I will write the equation till here. If I write the constant of integration at the end for the point P, I am not going to go till the end of the beam, which means the value of C1 will not be considered. So if this term, whose value you have seen in the previous question, was minus 154.51 or 56, something like that, if you don't take this value, which is quite large, then your answers are going to be wrong. So your approximation of the value of slope will be wrong. That's why it is written at the start and not at the end of the problem. Similarly, it happens with the point Q. For point Q, you take only up to this point for calculating the value of slope. So you are not going up to the end of the equation. So I hope I have made the point clear as to why we write the constant of integration at the start and not at the end of the equation. So now I'm going to use the boundary condition. Here I'll take the point A and point B. Obviously these are support reactions. So it means that there could be a hinge and a roller over here. So we have to take the boundary condition considering the point A and B. At point A, the value of x is 0. Since there is a support reaction, here I'll write down y is equal to 0. And for point B, where x is 3 meter, again I'll write down y is equal to 0. So I'm going to use this boundary conditions. I'll write down applying boundary conditions. The first one, at point A, x is 0, y is 0. So in this equation, when I substitute, the left hand side will directly become 0 is equal to C2. And I'm going to write the equation obviously till here. So I'll have plus C1 into 0 minus 15 into 0. I will not write the further two terms. So therefore I directly get C2 is equal to 0. Next one, at point B, x is 3 meter and the value of y is 0. When I substitute in this third equation, I get therefore 0 is equal to, C2 is already 0, so I am not taking this value, C1 into 3 minus 15 into 3 cube by 6. Now here I am going to write the equation till the end. So I have plus 60 into 3 minus 1.5 cube by 6 and minus 60 into 3 minus 2.25 cube upon 6. When I solve this, I get the value of C1 as 12.66. So I have got the value of C2 and C1. I'll substitute in equation 2 and 3. I'll get equation 4 and 5 for slope and deflection, where I have found the value of the constants C1 and C2. So therefore, when I rewrite the equation 3 and 4, I'll get EI dy by dx is equal to 12.66 minus 15x square by 2 from 0 to 1.5 minus 60 into x minus 1.5 square by 2 from 1.5 to 2.25, and I have plus 60 into x minus 2.25 the whole square by 2 from 2.25 to 3. I mark this as equation 4. Next equation is for deflection. EIY is equal to 12.66 into x minus 15 into x cube by 6 from 0 to 1.5 minus 60 into x minus 1.5 cube upon 6 from 1.5 to 2.25 plus 60 into x minus 2.25 the whole cube upon 6 from 2.25 to 3. This becomes my equation number 5. Now I am told to calculate the value of deflection at P and Q and slope at A. I'll first calculate for point A because it's just one value of slope. So for calculating the slope over here, I'm going to substitute the value of x as 0. So at point A, x is equal to 0. So when I substitute in equation 4, I get therefore EI dy by dx is equal to 12.66 minus 15 into 0. Now obviously I'm going to write only till here because that's what the equation is for A to P portion. Now EI value is known to me. When I substitute, I get the value of dy by dx at point A as 0.01507 radian. So this is the value that I obtain. Now here you need to just note that this value of EI in the question is given in terms of Newton mm square, and all the value of load is in kilonewton and the distance is in meter. So convert this into kilonewton meter square. Now when I have to convert, I'll just show you here. It is 8400 into 10 raised to 8 Newton mm square. When I convert this in kilonewton, it will be 8400 into 10 raised to 8. When I have kilonewton, it has to be divided by 10 raised to 3. And when I have mm square to convert into meter square, it will be again divided by 10 raised to 6. So this is 9. So this is the value, 840 kilonewton meter square. So just substitute here and you will get the value as 0.01507 radian. Next I will calculate the deflection for point P and Q. So at point P, the value of x is, you can see it is 1.5. So I'll write here 1.5 meter. For P, obviously the equation is going to be up to this point. So I'll write down therefore EI YP is equal to 12.66 into 1.5 minus 15 into 1.5 cube upon 6. When I substitute, I get the value of YP as 0.0125 meter. Now at point Q, the value of x is 2.25 meter. So when I substitute in the equation, I'll get EI YQ is equal to 12.66 into 2.25 minus 15 into 2.25 the whole cube upon 6. If you look at the equation for Q, I'll have to write up to this point. So I'll have one more term into this equation, that is minus 60 into 2.25 minus 1.5 cube upon 6. I get the value of YQ as minus 5.01 into 10 raised to minus 3 meter. So this is how the numerical is supposed to be solved. I hope you have understood the lecture. If you have any doubts, please write to me in the comment section. I'll see you in the next session. Thank you.